Hello guys, nice to see you. How are you doing? Hi, good, good. I'm doing okay. Yeah, I came back from my business trip. Was a bit busy and tired. This postponed lecture, which we had on Sunday, not many people attended, but um, that's obvious that some people couldn't because of your plans during the Sunday. However, the lecture is recorded and available online, so you can go through it. Uh, it was about damping oscillation, and we got quite detailed derivation of the final equation. So who is interested, and I believe for some of you, it would be interesting to go through all this derivation and understand how we finally get this equation which describes damping oscillation. However, it's not mandatory really to know how to where it comes from and how to derive it. So you just need to understand what it means and understand physical meaning of its terms, of all terms which are in this equation, like final equation for underdamped oscillation. Because there is overdamped oscillation, we considered that case 2. And that was a case when we don't have oscillation actually. It just any disturbance in overdamped oscillation when this friction force or drag force which acts on the oscillator is so high that instead of having any oscillating, it exponentially decays, and that's all. So this initial displacement. However, underdamped oscillations, they actually occur, and what happens that it has modified frequency different from initial frequency of string block system, like intrinsic frequency without friction, and the amplitude is exponentially decaying over time. So you just need to understand this equation and be able to explain the time dependence of the amplitude and difference in frequency because of damping from intrinsic frequency, which is square root intrinsic angular frequency of block string system. We considered that previously on our previous discussions, that is square root of K divided by amp, spring constant divided by mass of the block. So that is intrinsic frequency, and it will be modified because of the effect of drag force. So that is a short summary of our previous discussion, which is available online, so you can double check it if you're interested in the derivation of this equation. So today we start a new topic. So far, we were considering just like oscillators, and obviously if oscillator is in contact with some medium, it can create waves which spread in this medium. So wave is kind of interesting feature, like phenomenon, because it is capable of, like the main feature of waves is a possibility to transfer energy without transferring matter. So yet mechanical disturbance, periodic mechanical disturbance is spread along the medium. This periodic disturbance is created by an oscillator, and matter doesn't transfer through the medium. However, energy, which is transferred from oscillator to the medium, can move in space through the medium. So that is the main feature of waves. And our goal for this week will be to introduce the waves. We will start from the disturbance spread along a string, introduce types of waves, periodic disturbances, and start like deriving the wave equation, which will provide us whole information about displacement of the medium at any position at any time. So that is the main purpose of so-called wave equation, to get all this information. Okay, so maybe let me switch, like share my screen, and also switch to my slides. And now wait, I want to share my screen also. Okay, so let us consider first some disturbance. So it's single pulse, not a wave with its properties, but just single pulse. So if we have some string attached to a wall, so we can disturb this string, there will be one disturbance pulse, which is moving along this string. And in this, if, for instance, we have some simple harmonic oscillator attached to the string, so we can have periodic disturbances, and they will create already not just single pulse, but a wave which is moving along this string. In this particular case, the elements of the string, because of moving disturbance along the string, they move perpendicularly, in this case vertically, to the direction of spreading the disturbance, this pulse. So it moves from left to right, which is horizontal direction, and displacement of elements of the string will happen perpendicularly along vertical axis. So this type of waves would be called as a transfer wave, transverse wave, and represents certain type of waves which are possible in different media. There is another example of wave. So if we have such coil string and start to disturb it back and forth, so in this horizontal direction, then what it will create? It will create some compressed and stretched areas, like regions of this string, and this disturbance of compressed and stretched regions will move along the string from the left to right. So in this case, the elements of the string will move parallel to the direction of the disturbance propagation along the string. So this type of waves is called longitudinal waves. So there are two types of waves, transverse and longitudinal waves. And obviously in real life, there could be a kind of a mixture of both. So let's say one of the classical example of longitudinal waves are sound waves. So when we create some disturbance of pressure in atmosphere, for instance, we will result in, if this disturbance, for instance, is a periodic one, so we will create periodic regions with high and low pressure in air. And that disturbance will spread from the point of the origin of this sound in all directions, like in 4 pi sterradian. And what is important that the particles of our atmosphere will move, like these small elements of gas will move from lower pressure, so from higher pressure to lower pressure region in the direction of spreading the sound wave in atmosphere. So that's why this is classical example of longitudinal waves. There are other options when we have kind of a mixture of both longitudinal and transverse waves. And a good example is waves on the surface of water. Then some particles of water, they perform kind of circular motion during this, forming the waves on the surface of water. And there are two components. So a transverse displacement comes from the variation in the vertical position of water, so up and down, and longitudinal comes from moving back and forth on the surface of water. So it's kind of a mixture of both types. However, these two types of waves which are possible, they can classify a whole variety of waves which can be formed in any environments. So now, if we, let me stop sharing for a second. If we have some equation, some function, let's say y function of x, and here we put 0, which stands for t time equal 0. Let's say some fixed moment of time. Then it will be given with some function f of x. Why it happens? Because the shape, so we consider that the shape of the pulse doesn't change with time. So the shape of the pulse doesn't change with time, but it moves along the medium, along some axis x, for instance. And that's why at each given time, let's say t equals 0, we will have some function which will describe the displacement of each element of the string. If we are talking about some disturbance moving along the string as a function of x. So it will give us the shape of the pulse, which remains constant. So because the speed of the pulse, let's say, is v, so it moves with some speed along the string, then it will move, this pulse will move along the string with within some time interval t. There will be distance v times t. So if we come back to the shared screen, so we can consider such a system when we have a pulse along moving along the string. So here is some point P, which is just small element of this string. And we see that the shape of the pulse doesn't change over time. However, it moves. It moves from the left to the right. So after some interval of time t, it will move distance v times t. And that's why we can, for this any particular a point which we pick up on the string, any small element, we can write the following, that, let me stop sharing, this function which defines the shape, like this y function of x and time, position and time, which defines the wave x and time, will be equal to a function at x minus v times t at time 0. So if we want to know what will be displacement at a given point at position x, and after some time interval from 0 t, then we can consider the wave shape at time t equal to 0, but at different position where it was previously, because the previously it was shifted from the future position by this distance v times t. So x minus v times t provides us the information on the displacement of this given element of the string at coordinate x at time interval t. And if our pulse is moving from the right to the left in opposite direction, then this should be similar, but should be x plus v times t at time 0. So this function y xt is called wave function, which gives us the coordinate of any element of the string located at position x at any time. So our purpose is to figure out how we can derive this wave function, taking into account, for instance, some disturbance originated from a simple harmonic oscillator. Okay, so for this purpose, let us consider traveling wave. And traveling wave formed by simple harmonic oscillator. So something like, let's say we attach simple harmonic oscillator to the end of the string. It starts to oscillate, creates this wave which moves along the string. So if we show this model here, it will look something like this. So at t equal to 0, we have this position of the wave along the string. So it's displacement versus position x. At time t, after some interval, this will move by distance v times t along axis x. So we will have new position of this wave along this axis x. So if we count the number of seconds, like time interval, so if we plot displacement versus time, for instance, and count time interval between two adjacent points with the same phase, like say two maxima or just two minima, two maxima, or any other points in the same phase, that will give us period of this wave. And if we plot, for instance, displacement versus x position, the distance between two maxima or two minimum, they will give us the wavelengths. So wavelength is also the distance between 2 points, which are in the adjacent points, which are in the same phase. So we have definition of wavelength of a wave, and also its period. Obviously, guys will be related to each other via the speed of spreading the wave along this medium where it is generated. So we can write that frequency is kind of number of defines number of periods which can fit in 1 second. So it's 1 over t period. And if units for period is second, units for frequency is hertz. And it's second in the minus first power. So now let us consider some sinusoidal wave created by simple harmonic oscillator. And the shape of this wave at some time t equals 0 will be given as a times sinus small a times x. So it depends on position x, but at fixed time. So we don't have time here in the formula. A is the amplitude of the wave, and a small a in the argument of sinus is some constant to be determined. So we will work on this. So let us consider that at x equals 0, we have such situation y at 0, 0 for position and time. That will be equal to a times sinus a small times 0. And that will be equal to 0 because means sinus 0 will give us 0. The next value of x when y is equal to 0 is at x equal lambda divided by 2. So to make it more clear, if we look here at, let's say, x, y, here is our sinusoidal wave. So this is x0. Here will be x equal to lambda divided by 2, because lambda wavelength is from this point to this point, because distance between two adjacent points in the same phase. So that's why if we start from 0 with some sinusoidal, initially y is equal to 0, then next point when y is equal to 0 will be at x equal to lambda divided by 2, 1/2 of the wavelength. So now if we substitute, consider this value at x lambda divided by 2 at 0 time, that will be a times sinus small a times x, which is lambda divided by 2. And that will be also equal to 0, because we know it from here. So in this case, when this will be possible? It will be possible when this argument in the sinus, assuming that a small is not equal to 0, sinus will be equal to 0 only when small a times lambda divided by 2, the argument of the sinus, will be equal to pi radians. So it's 180 degrees. And from here, we can get this constant a is equal to a small is equal to 2 pi divided by lambda. So we define this small a. So now we can write that y as a function of x at given moment of time will be, so it actually gives us the shape of the wave at a given moment of time. It will be amplitude times sinus 2 pi divided by lambda times x, where lambda is the wavelength of the wave. And taking into account our previous discussion with this options for moving wave, assuming that the shape doesn't change over time, it just moves along the axis x, then if we have some wave traveling from left to right, then wave function y as a function of x and t will be given as amplitude a times sinus 2 pi divided by lambda times x minus v times t. So if the wave is moving from the right to the left, then we should put here plus instead of minus. But in this case, we already can quantitatively provide information on this wave function, complete information as a function of x and as a function of time. But we need to work further with this equation in order to adjust it and present in the final most common format. So let us consider first steps. We know from definition of the wave properties that wave travels some distance delta x, which is equal to lambda during the time interval, which is equal to period of the wave. So it's by definition of the properties of the wave. So we can write that v, speed of this wave, is delta x divided by delta t. So we can put it here, delta, some time interval. And that will be equal to lambda divided by period. So that gives us the speed of wave, which is moving in a given environment. In other words, it can be also given as frequency, because frequency is 1 over period times lambda. So now the argument of our wave function, we can change it in the argument of the sinus in the wave function. So let's write y as a function of position and time is equal to a sinus 2 pi divided by lambda Here is x minus, there was vt, but now instead of speed, we can substitute lambda divided by t. So let's do it. Lambda divided by period t times t time at which we want to know the displacement y. So we can put this lambda back in the parentheses, and eventually we will get a times sinus 2 pi times x divided by lambda minus time divided by period. So that is that actually shows us the periodicity of the wave, and we can claim based on this equation for the wave function that y, which is displacement of some element of the string, is always the same for every position x. Oops, sorry. Somehow there is some lagging in response to my pen. X plus lambda, x plus 2 lambda, and so on. And the same we can write for time, which is time t, time plus period, time plus 2 period, and so on. So we can actually show this because we can write the following: x divided by lambda minus t divided by period. Let's assume that we move with x by lambda and with t by period. So we claim that it should be equal. So it's x plus lambda divided by lambda, then minus t plus period divided by period. So this is actually this statement. So now we can see what is going on here. Will be x divided by lambda plus unity minus t divided by period minus unity. So these guys cancel out, and we eventually indeed see that it's equal to x divided by lambda minus time divided by t. So this form of the wave function indeed tells us that this is periodic, highlights periodic features of the wave, that displacement will be the same for every point in space and time, which is separated by lambda and period respectively. So now we can make some final modification of this wave function in order to present it in more convenient and most common format. So for this purpose, we need to introduce one parameter, which is angular wave number, k, and that is equal to 2 pi divided by lambda. So in this case, we also need to highlight the relationship between period and angular frequency. So angular frequency is equal to 2 pi divided by t. So now let us do the following. Let's write again the previous form of wave function. Yx t is equal to amplitude A times sinus 2 pi x divided by lambda minus time divided by period. So now if we put this 2 pi in parentheses, it will be A sinus 2 pi divided by lambda times x minus 2 pi divided by period times t. And if we already make these substitutions here, substitute instead of this k and instead of this omega, we will get more compact format of this form of this wave function. Will be A times sinus k times x, it's angular wave number, times position minus angular frequency times time. It is actually not the most complete form because it assumes that at time equals to 0, y is equal to 0. However, it's not, may not be the case, and we need to consider some initial phase constant. So the final format for the wave function, x, y as a function of x and t, will be A times sinus kx minus omega t and plus some initial phase constant p, which will tell us at which stage this wave is at initial moment of time t equals 0. So now we can describe the motion of any element of the string along which this wave is traveling, including velocity and acceleration in y direction of this element of the string, because we have this wave function. So for instance, velocity will be derivative, first derivative of y over dt at x equals to constant. So it's like partial derivative, assuming other variable, because there are two variables, x and t, but we take derivative over time, assuming x constant. So it's partial derivative of y over time, and that will be equal to minus omega times a times cosinus kx minus omega t plus phi. And with acceleration, a will be second derivative, like second partial derivative of displacement y over time, which will be d squared y over dt squared. And that is minus omega squared times a times sinus kx minus omega t plus p. So obviously we will have some maximum values for speed and acceleration. So we can write, let me clean here, that V maximum will be equal to omega times A when y is equal to 0. And acceleration A maximum will be equal to omega squared times A when y is equal to plus minus absolute, amplitude value of the wave. So max amplitude value of the displacement when this wave is traveling along the axis x along the string. So now, summarizing, we introduced, made the transition from just oscillators to waves, which can be created by these oscillators. So there are two types of main types of waves which are possible. Longitudinal, when particles or elements of the medium oscillate in the same direction as the spread of the wave, and also transverse, when elements of the medium oscillate, move perpendicularly to the direction of the wave propagation. So we define the types of waves, also main properties of the waves, which is wavelength, distance between two points in the same phase, and a period, which is time interval between two adjacent points with the same phase. Oh, there is a question: if V is velocity along y-axis, how do we know the sign is velocity up or down? I mean, it depends on the position x. So it will be, because it depends on the x and t, there are two variables, and based on at a given position, it will define either it is positive or negative velocity along axis y. And when we consider amplitude value, then we just don't care about the sign, we just consider only magnitude. Okay, good. So we managed to derive the wave function, which describes position of the elements of the string at any coordinate x and any moment of time t. We have shown that this describes indeed a periodic process, which means that y will be the same for all x and time with intervals of lambda and period, and also took first and second partial derivatives of the wave function in order to get equations which describe velocity and acceleration of the string element at any also position and time. With this, I think we can finish our today discussion. If you have more questions, you are welcome. And we will proceed further in learning more about waves during our future discussions along this week. And next time we meet on Wednesday. So thank you very much for attention. Have a good day. And see you next time. Bye-bye.
Thank you. Goodbye. Thank you. Goodbye.
You're welcome. Bye.